Yeah. Okay, well, we're going to get started here. Thanks everyone for coming. Evans, I'm an HPC Research Associate here at TAC. Our group consists of about 15 people, and TAC itself has maybe 130 staff members, but that number is always increasing. Part of our role as HPC Research Associates at TAC is to maintain the software environment that you work in, test out the hardware in the software environment, make sure it's working as it should. We also develop tools and things to help you guys run your programs more smoothly and efficiently. I think one of our defining roles as HPC Research Associates is we interface with our user community, which consists of different domain scientists and researchers. And what we like to do, or part of that role, is helping you guys come to grips with using our system, new types of hardware like these Manycore processors that are part of the Stampede KNL extension. You'll find, and I'll talk about this quite a bit this morning, that your serial codes, we have a lot of people that are running Python and R in like a serial fashion. And you'll find that they actually run not any faster on these processors, and sometimes even slower. And you might be thinking, or suspicious that, you know, we skimped on computer parts to save a buck or two so we could have Donut Fridays and Taco Tuesdays. But really, that's not the case. These are the state-of-the-art, and they are what things are going to be like more as we go into the future with processing, with computing. And hopefully I'll convince you why that's the case and why you need to start thinking Manycore. So first off, what is a multi-core or Manycore processor? Multi-core and Manycore definition, you've probably heard the term multi-core lots of times. It's in your laptops and everything like that. But all it means is it's a processor that has multiple execution units, which are typically called cores. And these cores are all capable of executing different instructions simultaneously. There's no real formal definition between multi-core and Manycore. Multi-core is usually on the order of tens of cores, and then Manycore is on the order of hundreds. This is a photo of a die of a Manycore processor. Actually, this is a KNL processor. And if you look closely, you can see the tiles, the different, each one of these different squares is a different core on the processor itself. So cores on a processor share resources. They may or may not share caches, which are a type of fast memory. Not share memory itself. Cache and memory coherence between these cores and memory has to be maintained by the hardware and the operating system in some way. So if I have some variable A, its value could actually be different in what's called the level 1 cache, the L1 cache, which I've labeled here. It could be different in between each of the cores, which each have their own L1 cache. And then that could even be different from what's in memory. And so the hardware has to somehow make sure that all of these values are correct at any given time so that your program is correct, so that you get the result that you expect and they don't get all jumbled up. Fortunately, you don't have to worry about this very much. The hardware handles it for you, and the performance of your software. So as an aside, why do we even use caches? Why don't we just use memory? Caches are smaller, much smaller than memory, say 512 kilobytes versus 100 gigabytes. They're much higher bandwidth, much less latency. You can have multiple levels of cache level 1, level 2. You'll often see LLC, which is the last level cache or the third level cache. And what they really do is help cores keep fed with data. So this little diagram here I have at the bottom of the slide, on the left we have our core, and it's so fast, almost as soon as it gets the data, it's crunching it. And so what it needs is to be able to pull data in at a rapid rate. But if it had to go all the way out to memory, it wouldn't be able to get that data nearly as rapidly. And so what happens is you get data that ends up in the L1 cache or the L2 cache in this diagram, and the core is able to access that data much more rapidly. And it's often the case that data gets reused, and so it's already in one of these caches, and you're able to perform more flops or more compute operations in a given amount of time. And what I'd point out here, and this is roughly, this is kind of rough, but it's kind of a decent rule of thumb, is you can get data from the L1 cache about 100 times faster than you can get data from memory. So anything that you have, any data that you have in there, helps your core run at a faster rate. So why do we have to go to multi-core and many-core? Why can't we just run, make the processors faster and everything like they had been since the 70s? So you all have heard of Moore's law. What it means is that the transistor density doubles every 2 years. As transistors got smaller, when they get smaller, they require less voltage and they require less current. And what this means is that they can switch at a higher frequency at the same power. The power that your processor is consuming is something like this expression I have here. P is proportional. The power is proportional to some factors in the front times F in red, the frequency, times the voltage squared. So as you decrease the voltage, you're able to increase the frequency of your processor and maintain the same power. So for years, for decades really, clock rates were increasing. You could slap more transistors on there to do tricky things like instruction level parallelism, which is an idea where instructions have to go through several steps in the processor before they complete executing. You can actually overlap these steps as they're executing. Out of order executions, OO executions, this is the capability of an instruction that is waiting for something like data to be superseded by another instruction that can jump in and run immediately. So it kind of sets up a queue that you can reorder these instructions in. Prefetching, which is just grabbing data before you need it, trying to predict what data that you're going to need, is another capability that they've been able to add, and it keeps getting better. And then SIMD units, which I'll talk at length later on in this talk. And also more cache. Like I said, cache is good. So what they were seeing with all of these different things combined was single processor performance was doubling every 18 months. This was great. Basically, you're getting double the performance for the same power. Life was good. I think back in like 2003, they were still expecting that by this time we would have 10 gigahertz processors. And wouldn't that be great? We wouldn't have to worry about all this parallelism. Our code would just run faster. But physics limits the single processor performance. We can still make smaller transistors. It's still being done. It's kind of slowing down. It gets more expensive every year. I read somewhere that the cost to fabricate and develop a new processor like doubles every time they come out with a new generation. So while the transistors are halving in size, the cost to produce these processors is doubling. And we also hit a limit where transistors can't really be smaller than atoms, like I think. Most people think that. And now the real effect though that we're seeing is that power is no longer decreasing as we shrink these transistors. So this expression I have here, the power of our processor is proportional to that term I showed on the previous slide, which they call the dynamic part of the power. That's the power that actually gets consumed as your transistors are switching or actually doing something. And then there's also this static power term, and that's power that's always being consumed by the processor, regardless of if it's doing anything. If it's turned on, the static term is contributing. And what's happening is as the transistors get smaller and the voltage gets smaller, this leakage, leakage here, the leakage current, they call it, is increasing exponentially. And so we are at the point now where we can't really reduce the power per transistor because that term is dominating. The static term is now the most important one. So we can't reduce the power per transistor anymore. More transistors have to be packed in the same area. When you do that, you end up with a higher power density, and then you're generating more heat. Faster processors than this, they get too hot. That heat is too densely located within the processor. So like a processor running at 3.8 gigahertz might be 171 degrees Fahrenheit, and that's pretty hot. Cooling this stuff gets to be bulky, impossible at some points. And what you end up with is what they call thermal runaway. So as the currents leak, that heats up the chips, and then that causes the leakage to even grow worse. So you just kind of slip out of control. And so the consequence is that speed hasn't really increased since 2009. As far as commodity processors go, 4 gigahertz is about the max that you'll see. Some people have overclocked their processors with special cooling to maybe 6 to 8 gigahertz, but that's about it. So the idea with Manycore or multi-core is to add lower frequency processors so that we can keep actually increasing our computational capacity and maintain that power envelope that we're looking for, and consequently the heat dissipation is reasonable. So some of the drawbacks with the multi-core and many-core is that performance does not typically scale linearly with the number of the cores. Even if the work that you're doing isn't perfectly parallel, or what they call embarrassingly parallel. This is because the cores, like I said, they share resources like the memory and the caches. They have to communicate with each other to maintain coherency between the memory and the caches. Adding that coherency then requirements that needs additional logic. So now you've got more logic steps involved with everything that you try to do. And this results in a longer latency between executions of different instructions. Prefetching and out-of-order execution can hide some of this latency. All modern processors are using techniques like this to hide some of that. But these are complex and so expensive that the improvement of them is really slowed down now. Coherency traffic is also using up all of the bandwidth, not all of the bandwidth, but it's using up some of the system bandwidth, and then so what you have is less bandwidth to actually move your data around that you want to operate on. Kind of intuitively, the memory bandwidth per core is also decreasing because you have some fixed amount of bandwidth. Now you've got to divide that between the number of cores. And that's going to be less than just the bandwidth divided by one core. And lastly, the individual cores have to be slower to maintain this level of power and heat that you're trying to maintain. And so what happens is serial codes might actually run slower on these newer processors. So why many-core over multi-core? Many-core is just a logical extension to multi-core. There's, like I said, there's no like hard and fast distinction, but many-core generally means hundreds of relatively slow, maybe 1.5 gigahertz processors versus tens of relatively fast 2.5 to 3 gigahertz processors. Overall, once you add all of this up, though, the number of cores and everything, what you get is more compute power available while maintaining the same amount of energy requirements for the processor to run. Manycore is really specialized for parallel computation, I would say, whereas multi-core is more general purpose, more for like running operating systems or general running websites and things like that. So in HPC, nowadays what we see is performance is really equivalent in some sense to parallelism. If you think about your laptop, probably it's got at least 2, if not 4 cores in it. It's still a multi-core processor. And a typical HPC compute node will have what we call 2 different sockets. I'll explain what that means. And each socket has its own 8-core processor. So this would be close to our Stampede system. But Stampede then also has, the Stampede compute node also has a nice corner coprocessor attached to it, which has, I think, 61 cores, in addition to the 16 cores in the 2 sockets there. And now with the Stampede extension, we've got 68 cores in each one of these processors. So the impact that this has on your software development, if you want to go faster, you might have to refactor your code. Some algorithms will actually run slower on Manycore because each individual, they're serial in nature, each individual core is a little bit slower. And then it'll be the case sometimes where an optimized serial code, you do some tricks to make it optimized, or some optimal serial algorithm is not parallelizable, and then you'll have to fall back to maybe a simpler algorithm, and not quite as optimized, but you can still parallelize in some way. What you really need to do, what really helps, is to use very predictable and linear code and data in your parts of your code that take the most time, the compute-sensitive kernels. So you need to do less of pointer chasing, like less function dereferencing and things like that. Less object-oriented techniques, which are great, but they're better for things like managing a workflow or staging your computation. And then also like less branches and conditionals. You want to make your compute-sensitive stuff as simple as possible so that the compiler can really help you improve the performance of it. And then finally, the main point is that parallelism is not really required to get improved performance of your application out of these types of processors. So what are some of the levels of parallelism? Like I said, in HPC, performance is all about stacking levels of parallelism. So the first level is multi-node. This is basically you have multiple individual computers that are all connected either by a standard Ethernet network, or our computers have a very fast network called InfiniBand. The new KNL system has yet another type of fast network called OmniPath. And the idea is each one of these compute nodes is in and of itself a computer. It has its own independent processors, its own independent memory. They each look like a single computer. The next level down is multi-socket. And you can have, like in Stampede, multiple sockets per node. So you can have 2 to 4 is typically as high as I've seen sockets per node. Sockets usually have they have one processor in them, and they have one physical memory located in them. As far as the user goes, the operating system kind of hides that from you. You can see it, and I'll show you implications of it on performance later. But for the most part, you can just run your code and not worry about this. The next level down is multi or many core. And this is the idea, like we've been talking about, having multiple cores per processor, where the cores share memory, and then they may share some levels of the cache. Then even below that now, there's hardware threads. And these are the idea of having multiple logical cores per physical processor. The KNLs have 4 logical cores per processor, and each logical core is sharing a single physical core. So only one logical core is actually able to execute anything on the physical core at any given time. There's a few operations that maybe they could do in parallel, but for the most part, you have to think of it as them only running one thing at a time. But they can kind of take turns and jump in for each other when one, for example, is waiting for data or is locked at a particular point in the code for some kind of reason. This is just kind of schematically what that looks like. At the top here, the multi-node level, I've got 2 nodes. Stampede has like 6,400. Like the KNL extension has 550, something like that. Then within a node, you've got your 2 different sockets, like on a Stampede, a node. And then below the sockets, you've got multiple cores within a socket. And then each core will have multiple of these hardware threads or logical cores. And then how the operating system, how you'll see it if you try to look at it, and you'll see examples of this later today, is the logical cores will just be numbered. They'll be enumerated 0 through the total number of hardware threads on the system. This is a kind of a neat little program. You can run this if you want on our systems. It's called LS-Topo, and it'll just dump out the topology of the processor that you run it on. This is from one of our Stampede nodes. And on the top here, the top big green rectangle, that's socket 0. The bottom one is socket 1. And then these gray squares are the numbers of the physical cores within the node. So you can see core 0 on the left, all the way to core 7 on the right in the top socket. And then in the bottom one, core 0 to core 7 in the bottom. And then within each of these cores, you can see the logical core number. You can see it varies from 0 to 14 in the top, and 1 to 15 in the bottom. Now, where this gets a bit more interesting is a processor like the KNL, which has 4 logical cores per physical core. This is the output of running LS-Topo on the KNL. There's so many cores that it gets a little bit difficult to look at. But if we zoom in on some cores here, we've got core 20 and core 21 zoomed out here in the middle. And they are in gray. And then you have the logical cores that actually live on those physical cores in white there. You can see there's 4. So like core 20 has logical cores 16, 84, 152, and 220 on it. So now I'm going to move on from the hardware, temporarily at least, to some of the impacts that this has on programming. And you've probably heard the terms multi-processing and multi-threading. I like the term multitasking because it incorporates those. Some of the basic concepts of multitasking are, first of all, the Linux operating system, it actually works on tasks. Tasks are just units of execution. Processes are tasks that have their own private memory, or you can think of as private data by default. And an example of this is you get two programs running at the same time. They each have their own data. They don't affect each other's data unless you do something else in order to make them communicate. Now, threads are just tasks that have shared memory or data by default. So if you've ever done threading with OpenMP or some of the other tools like pthreads that are provided by the operating system, these tend to happen at the function level. And threads actually, if you have multiple threads running, they can affect each other's data. One thread can change the value of a variable out from underneath another because they both are pointing to and seeing that same variable. And so you have to do things to make sure that your code is still running correctly, even when you're multi-threading. So multiprocessing is just processes executing in parallel, and multi-threading is just threads executing in parallel. There's also another concept, core and memory affinity, which we'll talk quite a bit about. And this is just the idea of associating tasks to cores and to cores on your processor, whether those are physical or logical, and the actual memory on your processor. There's contention for these shared resources. Like I mentioned, you've got limited memory, you've got limited cache and bandwidth out to these data storage areas on your processor. And you also have a limited number of physical cores. You can imagine just launching 1,000 tasks on a processor that only has 8 cores. Well, it's not going to go very well because each task is going to have to wait for access to that core. And then another thing, last concept is the idea of dependencies. Parallel tasks might be interdependent in some way. One task might have to wait for another one to complete before it's able to execute. And so this restricts the amount of concurrency that you can get out of a program. So in a practical sense, how do we run tasks in parallel? Once we've got ourselves a Manycore processor, well, there's a lot of different ways in Linux. I can't tell you about other operating systems, how they do it, but in Linux at least, you can easily, from the command line, run multiple processes simultaneously, or within a script, a batch script or something. As I show here, this example here. You start program 1, you use the ampersand sign, start program 2, ampersand sign, put all that on a single line, hit enter, and they will all start running in the, simultaneously. What the ampersand does is it just places processes in the background so that you're allowed to start others from within the same terminal, from within the same instance of the command line. Other ways you can run tasks in parallel is you can do what's called forking. That'll generate, they call it like a child task of a parent within your code. I would say you don't see this very often in HPC settings. There's also, I'll show you some examples of how to get multi-processing, where you're actually starting multiple processes from within the same code or script intranode. There's the pthreads library with the Linux operating system. Pthreads is just POSIX threads. That's how you can get access to really low level starting and stopping threads and controlling them on the operating system. But what people practically do is use OpenMP programming. And OpenMP just sits on top of pthreads, takes care of a lot of the data sharing, code correctness issues for you. And so these two approaches would allow you to start multiple threads on the same node. And finally, there's MPI, which you've probably all heard of. And basically what it's doing is starting multiple processes, opening up pathways for them to communicate. And this can be intranode within the same node, or it can be across thousands of nodes. We're not going to talk much about MPI today. We're going to focus on within a core or within a node types of programming, which is actually you get quite a bit of parallelism out of our new KNL processors because they have 68 cores on them. So we have these methods to run tasks on our processor, but which cores are these tasks actually running on? How does that work? How do we decide, where all these different tasks are running? When I launch this example up at the top, do they all get started on the same core? They get spread out in some smart way? Well, it turns out they usually get spread out in a pretty decent way. Linux has what's called a scheduler. And the Linux scheduler, the first thing I'll say is it treats processes and threads on the same level. They're just tasks to it. Tries to give every task a fair share of the processor's time. I think the name of the scheduling algorithm is actually called complete fair share. Each physical core has its own run queue on it. And runnable tasks are placed within a core's run queue. Tasks at the head of the queue, the guy all the way at the end, he gets run. He either runs for a maximum amount of time, which they're trying to give every task the same amount of time by dividing the length of time that they wait, divided by the number of tasks. So he either runs for that maximum amount of time, or he finishes, or he gets interrupted for some reason. Maybe you hit the keyboard or something like that. Now, after he's done running, a new task will get run on the core. The term for that is a context switch, but it's just a new task starting up on the core. And the old task, based on how long it got to run, it gets reinserted back into the run queue somewhere. It's not necessarily at the end, but sometimes it is, but it will get reinserted back in the run queue. So tasks get started on, how it's determined where tasks get started, which cores they get started on, or how they get moved around these cores is done by a load balancer that the scheduler has. So the Linux scheduler has a load balancer. It's run periodically. It's not run all the time because it's a relatively expensive operation. But what it tries to do is maximize the processor and cache utilization. It doesn't want any cores to be idle. If there's extra cache somewhere, or it'll want to place tasks on cores that are attached to that cache. So the idea is tasks can be moved from more busy to less busy cores. If I have 10 tasks running on this core, on core 0, and no tasks running on core 1, it'll shift 5 of those tasks over to core 1. The other aspect of this is that the load balancer tries to keep tasks close to the data. It wants to maintain what's known as data locality. The closer the core, the task is, the closer the core is that the task is running on to the data that task needs to operate on, the faster it'll have access to that data because of this memory hierarchy that we talked about. So what can happen is when a task gets moved to a new core, the local cache or memory on that core might not have the data that it needs. In this diagram up here, I have our memory hierarchy with 2 cores now, and they are sharing the same L2. Now, if task A moves from the lower core to the upper core, and its data is in the lower core's L1 cache, it's labeled data A here, it's going to have to get that data over to the L1 cache on the upper core, which currently is holding data B. And so what it might do is have to write that data back out to the L2 and then pull it back up into the upper core's L1 cache. Or I might even have to write it all the way up to memory in order to get access to that data. So this slows things down. Sometimes this is called cache thrashing. Basically, like I said, the idea is when it moves to another core, when your task moves from core to core, the task that it moves to might not have the data that it needs. This gets even worse if a task moves from one socket to another socket. The local memory on the new socket might not have the data that the core needs to run. And so what has to happen then is the data has to be transferred from the memory on the first socket over whatever interconnection the two sockets have. This typically results in like about a 50% longer latency. If you have cores, or if you have tasks all over the place, far away from their memory, you can run into limited bandwidth issues because they're all trying to get at their data, which is far away from them. In Linux, this is a consequence of what's called the first touch policy. The first socket that a task runs on is where the memory that it needs gets allocated. So you really want to make sure that your tasks are not jumping between sockets. And it's even better typically to make sure that your tasks are not jumping between cores. So how does load balancing work diagrammatically? Here I've got two different sockets in Linux. These different physical memories are called NUMA nodes. And that just stands for non-uniform memory access. So cores on NUMA node 0, it will take them longer to access memory than it will be to access the memory on their own node. So the idea that the load balancer wants to do is balance tasks across in such a way that data has to be moved the least. So it'll start off with trying to balance tasks at the bottom here. Say we have two tasks running on, two different numbers of tasks running on logical core 0 and 1. It'll try to balance across that first. And then if you have tasks running on the first 0 through 3 core, logical cores, it'll try to balance across those next. And then if you have tasks running on all of your cores, finally it'll try to balance across those. It'll try really hard to avoid having to move tasks far away from the NUMA node that they allocated their data on. So as you might guess, with a complicated setup like this, the load balancer is not perfect. You can end up with these this cache thrashing due to constantly switching context within a core, and tasks can end up on the wrong NUMA node. But what you can do, there's lots of techniques to pin tasks to sets of cores or NUMA nodes. So each task is given a set of cores that it's actually allowed to run on, and a pinned task will only float to cores that are part of this set. There's a lot of different tools for this, basically saying, okay, this task you can only run on cores 0 and 1. This task you can only run on cores 2 and 4. And some of these tools are NUMA control or NUMA CTL. That's probably the most common one. That's just part of any Linux operating system. As is task set. It's very similar to how NUMA control works. We'll play with some of these later. Sched set affinity, that's a way to set which core, it's a function call that you can make in your code that tells it to run on a particular core. And then in the OMP world, there is different environmental variables that you can set that determine where your tasks are allowed to run, which cores and which memory. So the most generic ones are OMP procbind and its friends. There's also GNU extensions to this, like GOMP affinity, GOMP affinity, and then Intel also has its own set, KMP affinity. What I would recommend and what you'll see is just to use the OpenMP variables because they're completely general. You can run them regardless of which compiler you use to generate your code. Hey.
We talked about the NUMA node as the node that's connected to other nodes via the InfiniBand or whatever.
A NUMA node is connected to other nodes via at least on our processors, but they're on the same compute node, right?
Okay.
You got your compute nodes.
Not a compute.
Right. Yes. Thank you. And then your NUMA nodes live within a compute node.
Okay.
They're able to talk to each other pretty quickly, but not as quickly as not having to talk to each other.
Oh, okay. Okay, I see. I just got confused about your description of what a node was. And
Yeah.
Mine was the compute node. So then I was wondering, node control that.
There's a lot of
across the or whatever. Yeah. Okay.
nodes gets reused a lot in the HPC
Okay.
world. But if you've ever heard the term Quick Path Interconnect or QPI, that's Intel's technology for connecting these NUMA nodes within. So 2 different sockets. Each socket is a NUMA node within the same process. And then every MPI implementation has its own set of affinity tools, and they can get relatively complicated, but really it's the kind of thing you go and you Google and you look it up. And we're not going to talk about MPI in any concrete way today.
So is this what the TAC affinity script that you all have those?
Yeah, TAC affinity will set up the way your tasks get spread in a reasonable way. It uses NUMA control underneath to do that. And then TAC affinity lets you, it rolls up some of this MPI affinity stuff in it too, and does a lot of this stuff for you automatically, so you don't have to worry about it too much. So let's move on to a little bit of performance. Talked about how we actually run things. Some ways that performance could be impacted, but how do we actually measure parallel performance? It's pretty straightforward, actually. You have a metric called speed up, which is just the run time of your parallel versus your serial code. How much faster does it go? I don't care how many tasks I'm using. I just want to see it go faster. And efficiency is the next metric that's commonly used. That's kind of like an efficiency metric. It's the speed up versus the number of tasks. How much speed up am I actually getting as I throw more tasks at this problem? And closely related to this, what impacts these metrics is a term called granularity. And this is just a fancy word for the amount of work I give each task to do. So we've assigned tasks to cores through some affinity mechanism, or the load balancers hopefully done it well for us, so that our tasks are chugging along. And once a task is assigned to a core, how do we, as a programmer, we have this work that we want to do, how do we divide that work among these tasks? So let's say we have a problem, we can break it into 10 parts that we can run concurrently, say like a Monte Carlo code or something like that. We have 10 cores and 10 different tasks. We'll break up the problem such that each task gets a part of that problem. Our affinity settings or our load balancer puts a single task on each core. The idea is that you want to ensure that all of your different parallel parts that you're running complete at the same time or very close in time. Otherwise, some of your tasks, and therefore the physical cores, the resources that you're getting charged SUs for, are going to be sitting there idle. This is load balancing from the programmer's perspective. This is the stuff that you guys are responsible for when you develop and run your codes. And the main idea is to minimize idle time for the tasks. And then this will maximize the amount of compute, the amount of science that you're squeezing out of the cores that you're being charged for. So now when I say load balancing, we'll forget about the Linux load balancer. It's doing that stuff in the background. We don't have to worry about that too much other than to correct its mistakes. Now load balancing will refer to the load balancing that you're doing when you implement your code. Like I said, granularity is the amount of work that you give each task. And it's important to balance the granularity to get parallel efficiency. Too much granularity can lead to load imbalance. So like I said, if you have idle tasks, that's not good. Well, you know, some tasks finish and they're waiting for others to complete. We don't want that. But too little granularity, too little work per task can result in overhead. And that's because these methods of parallelization are not free. It costs cycles to partition your problem. It costs cycles to decide what work gets assigned to what tasks. You also have to sometimes communicate data between tasks. And also synchronizing tasks. Like if they are operating on the same data object, you need to make sure that they're not stomping on each other, generating race conditions in your code, things like that. So let's look at a very simple load imbalance example just to see how this can work. So let's say we have some loop with 10 iterations. We're dividing it amongst 9 threads. I don't care what the work that it's doing, but let's just say each iteration takes a single thread, a single day. So what you have is 9 iterations are done the first day by 9 threads. Then 1 iteration is done the second day by a single thread. You've got, actually that should be 8 threads idle for the entire day. This results in an efficiency, if I just use that little formula that I threw up before, only about 55%. What's happening here is there's not really communication overhead affecting us, but we have a very poor load balance. If we had thrown 10 threads at the problem, it would have been done in a single day instead of 2 days. Here's a very simple example of parallel overhead. Let's say, okay, we've got a loop, 10 iterations, we divided it amongst 10 threads, great. The setup for the parallelization and maybe the teardown too requires a millisecond. Each iteration takes 1 thread, 0.1 milliseconds, let's say. So 10 iterations are done by 10 threads in 1 millisecond. The total parallel time that this took, though, is 2 milliseconds, whereas if I had just run it serial, it would have been done in 1 millisecond. So my efficiency is terrible. I think anything less than 10% means that you're actually going slower, or less than 50% means you're actually going slower than serial. And this is obviously something that you really want to avoid. So these might seem really simple, but they're simple instances, but they're demonstrating things that you might run into in your code. Okay, so let's take 5 or 10 minute break, and then we'll go on to vectorization, and I'll introduce that, and we can go through that. This will turn out to be a very important component of working with Manycore processors. So start up at 10, let's say.
If you've not signed in at the front desk, if you could please do that so they can keep track of who showed up today.
So, just go to portal. Go to training. If you scroll down. Get the new details. And if you're signed in, you can click on the link or the download link right there. Should work. Click that right now and see it. Yeah. That'll work for you. Okay, cool. Use the blue and the white. That's, sorry. And the afternoon session will be there as well, and under the other section. Okay, thank you. Does everyone have internet access? Okay. Okay. Where I can get you an alternate. I could give you like the specs as far as like whether it uses AES and that you can use less of my Yeah, I'm not sure. I mean, let's see if we can. Yeah, maybe you could figure it out. Yeah.
So can you hold on? Is there a way to measure parallel overhead?
Yes. So actually, if you do something like VTune, it'll automatically measure that for you.
Well, okay.
It'll just be called overhead.
All right.
How well a job it's doing, I don't necessarily know.
Yeah. Because I've experienced that my loop head doesn't have enough work. You know, the core of my loop doesn't. There's not enough math in there. Or something,
Yeah.
You know? So it shows the. You know, it's not very efficient, right? So when I throw some function calls, some sines or cosines in there,
Yeah.
it's just playing around, you know.
Yeah.
It jacks up the amount of work, and all of a sudden I get more parallels because I add cores or I add threads. So,
I think.
but I was just wondering if there was a baseline, a loop that does nothing requires, you know, a certain amount of. But I imagine there's memory management and all kinds of other.
That's where it gets really complicated, and as your problem size changes, you're pulling maybe more from memory than from your local caches. And,
Right. Yeah. There's I can imagine it being kind of calculation thing.
I wonder if the time command, when you run that, you know how it breaks into like a user and a system time?
Yeah.
I wonder if that system time is time spent in like the OpenMP runtime. That might be.
Could be.
Like a quick and easy place to see that. I don't know though, I haven't tested that out.
Anyway, I just wondered because I run into that all the time. It seems I just don't have. There's just not much, the finite difference or finite element
Mhm.
even. There's just not in the core. There's a few flops, right? A handful, 4 or 5.
Yeah.
And you can do loop unrolling and all that stuff to try to get more, better data locality and more operations, but still it's just not.
Yeah. You want to get the long loops.
All right, man. Vectorization.
Yeah.
The goal is, I don't know.
Okay.
Okay, I'm gonna start up again. It's 10 a.m. And this section is gonna give a brief intro to vectorization. This is yet another level of parallelism. As I said, in HPC, performance is practically equivalent to parallelism nowadays. The motivations for vectorization are very similar to the motivations for going to multi and many core. Basically, it's a way to squeeze out more flops at the same power level. So just the basics of vectorization. Cores have registers. Data needs to be in those registers in order for the cores to operate on them. So data gets moved from the cache or the memory into these registers. They get operated on, and they get moved back out to cache or memory. So for example, to add 2 integers, you first have to move integer A from the cache to a register. So in this diagram over here, each one of these blue squares represents a register. Secondly, you have to move a second integer from cache to a different register, in this case E. Then I have to operate on them. There's some logic in the processor that performs this operation. And then move that data, then I place that result in another register, A plus E, and move that data back to cache or memory. Like I explained in the previous section, frequencies are limited, so I can only do this so fast. If I have a 3 gigahertz processor, I can only do 3 billion of these per second. Sounds like a lot, but we don't want to get stuck there. So why not move the data registers and move and add multiple data simultaneously? Move the data to the multiple data to the registers simultaneously, and then add those simultaneously. And this is what they call SIMD, or single instruction multiple data. So the idea is just make your registers wider. If my previous register could only hold a single data element, why don't I just make my register able to hold 4 data elements? And so you can see, generally, the idea here is my wider register, I have a wider register at the top, one in the middle. I can add all 4 of these, do all 4 of these operations simultaneously, store them out to a register simultaneously, and then you can actually move all of this data out of the register to cache simultaneously. So we're really getting, almost in a sense for free, an additional number of computations per cycle. So now instead of only being able to do 3 billion flops per cycle or per second, I can do 12. This approach, especially recently, has gotten a lot more popular. And you can guess probably why, is that cores aren't getting faster like they used to. Individual cores aren't getting faster like they used to. Since before 2010, the vector lengths actually increased by factor of 4. So over here on the right, I have the types of data that these registers operate on, that these registers can hold and operate on. And when you see SP throughout this talk, I'm referring to single precision, and that's going to be 32-bit numbers, and double precision, that's going to be like 64-bit numbers. So in like C, a double is going to be a 64-bit, and a float is going to be a 32-bit number. You can see the ISA is the instruction set architecture. It's just a fancy name for the types of instructions that are used to perform these vector operations. And you can see we've gone from MMX, which I think is multimedia extensions, which is just for like streaming video and whatnot. Back up to now we have 512-bit registers. So these can actually hold and operate on 8 double precision vectors simultaneously, or data elements simultaneously. So different types of processors have different width vector registers. Pre-Sandy Bridge processors, Sandy Bridge is what we have in our Stampede system, were SSE or SSE 2, 3, or 4, they're just slight extensions to each other. Those were only able to operate on 2 double precision data elements simultaneously. With Sandy Bridge, this vector register width was doubled, so now we can operate on 4 data elements simultaneously. AVX is, that's what's on Stampede. AVX2 then, if you've heard of our Lone Star 5 system, that has Haswell processors, and they have an AVX2 instruction set. What's cool about the AVX2 instruction set is that it has what they call a fused multiply instruction. So it will actually be able to perform, it'll be able to multiply a number times another, and then actually add another number to that all in one operation. I don't know the details of how that's done, but the idea is that they're able to even double the number of flops for operations that require a product and an addition. So like anytime you multiply a matrix times a vector, you'll see this. And then in the bottom is our AVX 512 instructions. The Knight's Landing processor has these mic-avx-512 instructions. Newer processors that you'll see soon will have just plain old AVX 512 instructions. As I said, they're able to do 8 double precision operations simultaneously. Now you have to use the correct vector instructions to use these registers. So of course, vectorized code uses vector instructions. Vector instructions actually operate on multiple data elements simultaneously. There exist vector instructions for moving and operating on data. So over here on the left with the yellow boxes, I have my cache lines. The idea is a single vector instruction will move 4 data elements from a cache line into one of my blue box registers on the right here. And then another move instruction will move 4 elements from the cache line to another blue box instruction. Then I'll add those 2 together with a single instruction. And at the bottom there, the data will be stored there and then moved back into the cache with a single instruction. Kind of how you can think about vectorization and more or less what the compiler does when it vectorizes your code for you is a for loop before vectorization I have at the top. We're just iterating over I and adding 2 arrays together and storing them in array A. After vectorization, you can think of this loop as being unrolled. So if I had a vector length of 4, now I have all 4 elements, and the vector instructions will operate on those 4 elements, do these 4 operations simultaneously. So an ideal speed up due to vectorization, if you were to assume that your whole code was perfectly vectorized, this never happens, but wouldn't that be cool? Speed up is just literally, it's proportional to the vector width. So SSE can do 2 double precision, so you would get double the speed. AVX can do 4 double precision operations simultaneously, so your speed would increase by 4. And AVX 512 would increase your speed by 8, because it can operate on 8 double precision simultaneously. So let's just calculate the theoretical peak for Stampede KNLs. We've got 68 cores on there. Another wrinkle is that each core actually has 2 what they call vector processing units. That is 2 units that are able to operate on data that's in these vector registers. And it can do it simultaneously. 8 flops are being performed per BPU cycle. And then I multiply that times 1.4 billion cycles per second, which is roughly, that's the nominal speed for these processors. And then I end up with about 1,500 gigaflops. I toss in the fused multiply wrinkle, because now, fuse add multiply, because now I'm able to multiply and 2 numbers together and add another number together simultaneously. And that bumps up the theoretical peak of the KNL to 3 teraflops. And you can go through this exercise through any of our machines' processors and get different results in a similar manner to this. And this is like when you see the peak flops that a machine's capable of producing, the theoretical peak this is how they're calculating that. There's all kinds of caveats that go into this that prevent you from actually being able to achieve this. It's just very hard to keep all of these vector processing units busy because you always have to be pulling more and more data from different levels of the memory hierarchy. And that always takes longer than it does to actually perform the operations once the data gets there. So what are some of the, like I was just talking about, some of these deviations from the ideal? And these all apply to multitasking too. You'll have deviations due to bandwidth limitations. If you're not utilizing your cache perfectly, you've got to wait for data to come from memory. There's also an issue called alignment, which I don't think I'll get into, but it has to do with how your data actually lines up on the vector registers. And then also due to Amdahl's law. Like I said, you know, the perfect speed up would mean that your whole code was vectorized, but that's really impossible because any code that you're running will take some total amount of time, which will be equal to your parallel time, the amount of your code that's parallelized, plus the serial time of your code. And the P here, dividing the T sub parallel, is just the number of processors that I'm using. If that T sub parallel divided by P goes to 0, I still am stuck with my T serial. And the serial portion of my code is not getting any faster through vectorization or through multitasking. So at the bottom here, I just have a diagram of what you can expect based on the percent of your code that's vectorized. The triangles here is if your code is 90% vectorized. But a vector width of 16, I still would only get a speed up of about 6 times. And then it gets progressively worse. At 30%, I get not even a double speed up if I'm using 16 vector width registers. So some general guidelines for how to vectorize your program. Turns out conveniently that it doesn't require a whole lot from you if you follow these guidelines. The first approach that you might do, if you're crazy, is write the code in assembly, or write the kernel that you want to compute in assembly. It's generally a bad idea unless you're a robot. It's going to be error prone. It's really hard to get this stuff right. It probably won't be that fast because it's just really hard to get this stuff right. And it's not going to be portable at all. As soon as you try to run it on a different architecture, it's not going to run because you're using instructions that architecture doesn't have. Intrinsics, which are to the C language that maybe the Intel compiler or the GNU compiler supports. Basically, they're little functions that you can call in your code that are very close to assembly language, but they prevent you from making a lot of the mistakes that you might have if you were to try to do the assembly on your own. I would say this is less error prone. You're probably not getting the best performance that you could using these unless you're really good. Some people do, and they do great with it. And it's still not portable. As soon as you try to run it on a processor that doesn't support that particular intrinsic, then it's not going to be able to run. So you've written software that only runs on this one processor. It's not usually a good investment of time and money. The next one, which I would say is often the best idea, is to just use compiler flags. Basically, you just tell at compile time, you just tell the compiler to use a particular instruction set, and it'll go ahead and do it. It'll do typically a great job optimizing, especially if you followed some of those guidelines where you made your compute-intensive parts of your code relatively simple and straightforward. The compiler has all kinds of different heuristics and ways that it can look at that code and decide how to optimize it and vectorize it just for you, as long as it's simple and straightforward. The best you can do, so say you're doing like matrix decomposition of some type or different linear algebraic operations, is to link to optimized and vectorized libraries. These have had like teams of scientists and engineers that have been working on this stuff for decades to get it performing really well. It'll be very portable. It'll even be optimized for different processor architectures that you run on. It'll have multiple types of branches of code that'll be able to run on one processor optimally, just as it can run on another processor optimally. Intel's math kernel library is something that you have probably heard of. It's usually called MKL. This is an example of one of these optimized libraries. Actually, something which you'll see in the lab, MKL can also do multi-threading for you automatically, and that's pretty great. It can really help you get performance out of your code relatively straightforward. So these are what these different compiler flags look like. On the top I have Intel, and -02, that's the optimization level. It goes 0 through 03, where 0 is the least optimized, 03 is the most optimized. Intel's default is 02. That'll give you access to the SSE2 instruction sets. Remember, those are 2 double precision operations simultaneously. You can also toss it AVX. That'll get you the 4 double precision simultaneously. Remember, it has to be a processor that's capable of running AVX instructions. Same for AVX2. Core AVX2 is just another label for AVX2. And then Mike AVX512. That's currently the widest registers. That's currently the instruction set capable of operating on the widest registers. That's only available on the KNLs. A convenient option is just to use Xhost. Maybe I should have just started off with that one. It chooses the most advanced instruction set available to you. You'll see, though, that that can be a little bit tricky with our setup on the Stampede KNL extension. Now, GCC I have here on the bottom, the -03, gets you your SSE2, a little bit different than Intel. You won't get any vectorization at lower levels. And then it's got its own equivalent of AVX, AVX2. Getting the AVX512, actually, you have to include these 4 different flags. It's not as pretty as the Mike-AVX512, but it's what you got to do in GCC. Or you can also do, similar to Xhost, -M architecture equals native. Whatever I'm compiling on, use the highest level instruction set that it has. So, main ideas behind vector-aware programming. Most of your vectorizations opportunities are going to be in loops. You want to keep the loops simple to help the compiler. You want to evaluate performance improvement after your vectorization. Consider your memory access patterns. I think I'll mention this later. More about that later. Use the different vector math libraries that are available to you. Okay, we're not going to cover this next section. I'll move on to just an intro to the KNL hardware. And this is the actual hardware that you're going to see here when you are running through the lab. So basically, our Knight's Landing extension to Stampede has the Knight's Landing or KNL processors. You'll also hear them called Xeon Phis. The idea behind them is that they just use a normal x86 architecture like all of Intel's other processors. So it's binary compatible with the new one, with these new processors and the old ones. Got relatively simple cores. They have reasonable serial performance. They're not terrible. It supports your standard old programming models, which is maybe a benefit compared to using GPUs, where you have to use special language just to even interact with that hardware. It's designed really for floating point performance in parallel. An interesting wrinkle is it provides this high memory bandwidth memory called MCD RAM. And then it also has a bunch of your regular old DDR memory to provide the capacity. It runs its own operating system, so it feels like a normal node that if you've logged into our systems before. And it's designed to run hundreds of threads in parallel. So just a quick architecture overview. The nominal KNL processor has up to 72 cores. Each core has its own L1 cache. There's four hardware threads per core for a possible total of 288 threads. Now our processors actually only have 68 cores. And that's just a consequence of how many cores come out well during the die process. And 68 is about where they're landing right now. So there's 2 cores per tile. So there's a set of tiles on the processor. So we have like 34 tiles in our processor. I'll show you a little bit more about that in a second. They share an L2 cache. There's actually like you can think of it as a 2D mesh interconnect. Think of it as like a grid that connects all the processors with each other. This fast RAM, called multi-channel RAM or MCD RAM, is 16 gigabytes. The nodes have 100 gigabytes of DDR. DDR is just regular old DRAM. Single socket, like we just computed, as 3 teraflops of double precision performance. It's able to get a really great memory bandwidth out of this MCD RAM, 450 gigabytes per second. And it supports Intel OmniPath Fabric, but we won't be talking about that much today. So if you're familiar with the KNC, which is the coprocessor that's on our old system, there's some distinctions between the KNL and the KNC. Basically, you can think of everything about the KNL is better. It's faster. It's got more memory. It's self-hosted. It has 2 vector processing units instead of 1. It's capable of out-of-order execution. It can do things like branch prediction, which is like when you get to the end of a loop and you decide whether you want to go back to the start of the loop or finish the loop. And it can do pretty much everything's a little bit better about it. This is just the schematic of the processor. As I said, the cores are grouped into tiles. 36 possible tiles. Stampede only has 34. 2D mesh interconnect. So you can see in this diagram, the blue squares are the tiles. There's 6 channels to DDR4, which are these orange arrows going out to the left and the right of the processor. And then 16 gigabytes of MCD RAM that are spread out around the chip in these yellow squares, MCD RAM. Each MCD RAM chip has EDC attached to it. That's the controller for the memory that's in there. And each of the 3 channels for the DDR has its own memory controller. It's kind of like what, just a diagram of the KNL tiles. So on the left and right, we have our cores. In the diagram at the bottom, each one has its own L1 cache. Each core has 2 vector processing units. These cores are connected to each other. There's some interconnect, which is just called a hub in this diagram. And they share an L2 cache, which is a 1 megabyte cache, L2 cache. Already talked about the instruction set architecture. Basically, the KNL has additional instructions for these 512-bit operations over the previous Haswell and Sandy Bridge architectures.
There was a question online referring to slide 38. Why not use -0 3 3 for the Intel compiler as opposed to?
Okay, there was a question online about slide 38. Why not use -03 for the Intel compiler? And you certainly can. I was just showing that -02 is where you get access to where the compiler starts using vectorized instructions. It's worth trying -03. I actually find that -03 often does not result in faster code, even though it's supposed to be a higher level of optimization. But it's worth checking both of them. So a summary of what you find on a KNL is it'll run all the stuff that you're used to, Fortran, C, Python stuff. It feels like a normal node. However, it's got this many core approach, which means that the cores are relatively slow, and you really need some kind of level of parallelization to get good performance. It's binary compatible, so you can take the codes that you've compiled on Stampede nodes and run them on KNL nodes. But you can't take code that you compiled on KNL nodes and run them on Stampede nodes because they have additional instructions that Stampede doesn't understand. Talk a little bit about the memory architecture on these chips, or on these processors with this fast RAM that I mentioned. So we've got 2 different memory types, DDR4, which is it's actually a very fast version of your plain old DRAM memory. It's the newest one out, but it's just like your normal memory that you're used to working with. And then MCDRAM, which is much faster, much higher bandwidth. There's 3 different modes that you can actually boot these processors in. They're called cache mode, flat mode, and hybrid mode. Cache mode, what you have, I have it up on the top here, this top diagram. Your MCDRAM is almost acting like another level of cache. So you have your first 2 levels of cache, L1 and L2, on these processors. But MCDRAM is in the middle now, acting as its own form of cache. It's completely transparent to you as a user. You don't really have to worry about it. When you run your code, it'll try to allocate itself into MCDRAM automatically because it's faster. It's generally a good way to go. That's the kind of nodes that we'll be playing on today. There's also this mode called flat mode, and it's where in memory space, the MCDRAM and the DDR4 are actually separated. So you can see this when you're programming or when you're exploring around on a node. They're actually going to be labeled as 2 different Newman nodes. MCDRAM will be Newman node 1, and DDR4 will be Newman node 0. So when you run your code, you could say, hey, I want to pin my code to Newman node 1 when it runs, because that's going to be where the fast MCDRAM is. And then finally, hybrid mode is just a mixture of the 2. There's different levels of mixing it. So you still have access to being able to pin your code to MCDRAM or DDR4 if you want, but then MCDRAM, there's some level of cache there that you can take advantage of as well. It's kind of a in-between. Yes?
Can user take explicit control on MCDRAM?
So in flat mode and hybrid mode, the user can. What they do is you pin your task to Newman node 1. So for example, you could do NUMA control -M1 and then your code. And I think I have examples of that in the lab. And then that'll pin your job in MCDRAM and it'll run from there. You can also do it from within your code. There's a different, if you're familiar with C programming's malloc,
yeah,
there's a different version of malloc that you can use. I think it's called HBW malloc.
For MCDRAM?
Yes, yeah, and that'll allocate that array or whatever object it is into MCDRAM for you automatically. But that's only available in flat mode or hybrid mode. Cache mode does not have a concept of the separation of memory.
Is it
Is there any advantage to use cache mode? What is the benefit to the user?
The reason for, you have to do less work to get it to run well. The data, MCD RAM is pretty big, right? It's 16 gigabytes. If I'm running in cache mode, my program takes less than 16 gigabytes, I don't have to do anything and everything just ends up in MCD RAM for me. I just run my program, it goes super fast and I'm happy. If I want to do more work, I can decide, or my code needs more than that 16 gigabytes, right? If some of the data that I need it to come in very fast, I could allocate it in the MCD RAM. And some of the data that I don't need so much, I could just leave it in DDR4 and not worry about it. Yeah, so like I said, MCD RAM acts as a cache. It's what they call a direct map cache. You don't have to worry about what that means, really. It's transparent to you and your software. If you have a cache miss, the main drawback is if you have a cache miss when you're running in cache mode, and it has to go to DDR4 to get that data, it can take a little bit longer. Now this will just look like a single NUMA node to your operating system and to your programs. This is if you're running in flat mode. Like I said before, you've got your 2 different NUMA nodes. You can use NUMA CTL or that HBW malloc that I mentioned function is defined in Intel's memkind library. So you would have to link to that library in order to get access to those functions. And like I said, hybrid's kind of something in between. So these are pretty complicated, and we found that they're generally not relevant, this concept of cluster modes. It's just a different approaches to organizing where the memory lies in the processor. And I'm not going to go through these details today. But they're there for you in case you're interested.
Quadrants minimize the cost of a cache miss.
Yeah, basically quadrant reduces the cost of missing in the L2 cache. It brings the guy that knows where the data is closer to the data itself, basically. And most of our, if not most of our nodes are run in quadrant mode because it turns out that's the fastest mode for most applications. That's the one Intel recommends for general computing. And so that's kind of where we landed in our benchmarking, is to use this quadrant.
So it has another layer of hierarchy.
Quadrant mode does not. It is actually invisible to you and your program.
So you don't have to scale your program maybe for section.
No, there's another mode called subNUMA clustering, where it is kind of broken up into, you can think of it as 4 different NUMA nodes. And we do have a couple of nodes set up in that configuration, but it's tricky to get good performance out of it because you have to place your tasks in the right nodes to see that performance increase. And even if you do that, I don't think we've seen a lot of improvement in performance. Okay, so talk about all these logical processors and how they're laid out. BIOSes can vary, but on our processors, we've got 68 physical cores. Each core is 4 hardware threads, so there's 272 logical cores. And cores are labeled, like the first set of hardware threads are on physical core, they go 1 on each physical core. Then the second set of hardware threads, you add another 1 to each physical core, and so on until you've got 4 hardware threads per core. So for example, core 0 has logical cores 0, 68, 136, and 204 on it. Usually you don't want to use all 272 cores. And actually, this shouldn't say 272. If you're using less than 68 cores, you want to watch out for Things like node imbalance, because some of your cores are going to be idle. Here's just a diagram going through what I just said there. This is only showing 64 of the cores, but the physical core number is along the bottom. Core 0, core 1, core 2 through core 63. And then each one of these physical cores has hardware threads assigned to it, or logical core numbers assigned to it. So in the first row, 0 through 63, the second row, 64 through 127. So you can see in this example, I have hardware thread number or logical core number. They're interchangeable terms, 0, 64, 128, and 192. And again, this is what that, like, if you were to look at LS topo and zoom in on the first core on one of our systems, you can see that core 0 in gray has these logical cores 0, 68, 136, and 204 on it. So why do we care about this task to core affinity? The hardware is complex. Cores, 4 hardware threads per core, different memory modes, etc. The balancer can float tasks around cores. The big problem is the cores might lose data locality. Multiple tasks can be running on the same logical core, leading to load imbalance. Like I said, there's a lot of different affinity methods to avoid this. As I mentioned, OpenMP has different ways to specify these affinities. We bring up OpenMP a lot because it's one of the most common ways to achieve parallelism within a node, within like a multi-threading paradigm. OpenMP, Intel, and GNU have their own environmental variables that can be set to achieve parallelism. But I would say OpenMP is really the most portable one. It'll work regardless of which compiler you use to build your code. There's 2 main ways to set thread affinity with OpenMP. And the first one's called binding policies, which is kind of a simple general approach. And then you can use something called binding places, which can be simple, and it can also be harder if you're trying to get finer granularity. And you'll see examples of this in the lab. Yeah, I won't go through. Well, let me just mention. So the OpenMP process bind, proc bind, there's 3 different ones. Really, you just use either close or spread the first 2. Close packs the threads close together. So threads that are closest to each other in terms of if they share an L2, thread 0 through 1 would end up on the same physical core, for example. Spread apart means they're trying to spread the cores as far apart as possible across the memory hierarchy. So if you had 2 NUMA nodes, core 0 would go on NUMA node 0, or task 0 would go on NUMA node 0, and task 1 would go on NUMA node 1. And you just set them by setting these environmental variables here. Export proc bind equals close, or export proc bind equals spread. Places isn't so interesting. We have a lot of slides here that are here for your reference that show where hardware threads will end up by default in OpenMP, and you can refer back to these when you're doing the lab if you like. If you use the spread setting or the close setting. And just a comparison of those 2. So now let's move on to the introduction to how KNL is set up on TAC and the lab itself. Okay, so we've got these racks coming in right now. I think we're getting, they're coming in groups of 6s or groups of 10s over the next couple of weeks. We're filling up our data center. You can see each one of these is a rack. just have each, and there's multiple KNL processing nodes just stacked together on top of each other in these racks. And they can all talk to each other through the switch in the middle, which is the Intel OmniPath switches. So this upgrade cluster that maybe some of you have been working with should get about 1.5 petaflops of additional performance. It rated in the top 500 is 117. This is just the upgrade right now, 504 of these KNL nodes. Stampede 2 will have obviously quite a bit more, I think several thousand. Currently, it is a separate cluster from Stampede, kind of a standalone cluster, and but it does share file systems, so you don't have to move your data or your codes from one to the other at this point. They both point back to the same file system. And it's achieved through one of the advanced cyber infrastructure grants funded by the NSF. So the general layout of the upgrade. At the top is the old Stampede original cluster, all of its Sandy Bridge nodes. Now when you log into Stampede from the internet, you'll land on one of our login nodes, logins 1 through 4. And then from there, you can start you can submit jobs through the SBatch mechanism, which just kind of sends your jobs off to the node and they run, and then they dump some output. Or what we'll be doing today is this IDEV mechanism, which is a really nice tool that they've set up here that will start an interactive session for you on one of the nodes. So at the bottom here is the KNL upgrade. When you log in, that'll put you on, there's only a single login node, login-KNL1. Then from there, you can either SBatch or IDEV to the KNL compute nodes. The biggest wrinkle here, which might confuse or trip some people up initially, is that the login node is actually a Haswell, whereas the compute nodes are KNLs. And if you recall, I said they have some of the instruction sets aren't compatible with each other. The reason that the login node is a Haswell is because Haswells are much more multi-purpose. They can handle a wider variety of workloads, whereas the KNL compute nodes are really specialized for parallel types of operations. Now, if you're logged into either Stampede at the top or the KNL cluster at the bottom, you will still see the same home, scratch, and work file systems. So anytime you jump from one node to the other, or from one cluster to the other, your data is still there, you can still see it. So what's the next step? It's going to be Stampede 2. It's going to be 18 petaflops. It'll be some more standard type of Intel Xeon, a relatively small number of those, plus these KNL processors. It'll be connected through the OmniPath Fabric network. It'll have this new type of non-volatile memory, although I think that's a year or two away before that'll be ready. So we're not going to worry about that. The racks are coming in right now, though. So we're going to have Manycore here at TAC for quite some time. So now we'll start with the interactive stuff. Basically, I just need you guys to log into the login node. So you'll SSH the username at login-knl1. That's stampede.tac.utexas.edu. Then you'll have to enter your password and the TAC token thing. Extract the lab from this location. It's just called that. Just untar it into your home directory, and then jump into the directory that we've untarred. So I'll give everyone some time to sort this out, and let me know if you're having trouble accessing the nodes or the training material. So do they need tag tokens in there?
They have to have their account set up.
They have to have an account.
Distributed.
Okay.
Perfect. We can't really distribute that to webcasters. If they're in
Mhm.
room, I mean, I can go grab the training account.
How does that work when you need a token?
I've got a set. I've got a hard coded token for a group of like 50 to 100
Okay.
accounts. So Patrick set it up for me.
Okay. I don't know if that would be a problem today. Now, can they access this lab somewhere?
It's available on the train. So if you go to
Oh, no, I'm just-
portal.high.texas.edu/upcoming training, you can download it by just going into the.
So you guys can go through it at your own pace if you want.
And then go to view details. And then just hit the blue and white link to the right of the file name,
Mm-hmm.
and that'll pull the file down.
Okay. Yeah, so if you guys want these slides, specifically this, these labs here, you can go to this link up here on our website, and then just download the intro to KNL _tac.pdf.
They may get a permission error if they click on the name of the file itself. So
Okay.
use the blue and white link.
Yeah, click on the blue and white download link on the right.
If anybody has any problems signing in to Stampede's KNL, just raise your hand and we'll help you.
Okay. I'm going to move forward and do some of these explore slides kind of interactively with you guys. If you want to get started on the lab stuff, that's all under the exercises, just labeled with EX 1 through 6. But I'm going to run through some of this interactively if you care to follow along. Okay, so let me make this bigger actually. When I log in to the login node, like I said before, I'm on a Haswell processor. And one way that you can view this is Cat just dumps out the contents of a file. I can just dump out the CPU info. What you'll see over here is there's 27 different processors. So I know that I am not on a KNL, which should show 272, right? If you know enough about how these things are labeled, this V3 here indicates a Haswell processor. Not that you need to know that, but if you're ever wondering, hey, am I on the login node or compute node, you can either look at this prompt here, which you may or may not have depending on how your bash terminal is set up, or you can dump this file and see, okay, there's not that many cores on here, so I must be on a compute node or a login node. Do what?
Can you make that?
Like that. Another thing you can do, you can see all the different queues. We use the Slurm scheduler. You can see all the different queues by typing sinfo. And so you'll see things like flat, all-to-all, flat quadrant, and normal. Normal corresponds to cache quadrants in our setup. And then the other ones, flat, as you've heard, is different memory modes. And then the all-to-all and SNC are different types of cluster modes, which you don't really need to worry about too much. And the idea is each one of these queues only has nodes that have been booted in that particular mode. You can't change these modes on the fly. You have to do it at boot time. And then if you're familiar with our module system, you can see what modules you currently have loaded. If you type the command correctly, you can see what modules are available to you. Should dump a whole bunch of stuff. So that's part of the software environment that we try to maintain. Now, here's something would be great if everyone does give a shot. And that's compiling a fat binary executable. So this will be an executable that's capable of running on multiple architectures. They call it fat just because there's actually extra code in there and it takes different branches based on what type of processor that you're running on. So if you want to just go ahead and start with some of these steps here, it's kind of where the lab really begins. And then I'll let you guys work through the fat binary stuff at your own pace, connecting to a KNL node, and then just ask us for any questions that you run into.
I guess I'm just sometime.
No, I waited until you got here.
Oh. Were you able to understand my crude remarks?
Yeah, they're perfect.
Good, thanks.
Yeah.
Alright, now you can go back to this slide. You're okay.
Okay, this is Todd, the presenter. I just wanted to make a clarification with the labs. They're just self-paced labs. Please just work through them and ask us questions if and when you run into them. If there's mistakes in them, just let us know and we'll do our best to clarify them. Thanks. I've had a request to clarify the Python exercise, exercise 3. If you do not do module load Python, you will be using the system Python, which does not have any parallel performance enabled in it. So please make sure for the Python exercises that you first type module load Python to get our build of Python that is optimized for the KNLs. Okay, so for everyone that's been following along online, we're going to take a break right now for the next hour. Some of the people are going on a tour of the machine room. Some people are grabbing lunch. But the advanced section is going to start up again at noon, or sorry, at 1 p.m. And
We're not going to be using this presentation, so we're ending this presentation.
okay, we'll be ending this presentation and using the other link for the advanced section.